to be working on solutions for the Specialist Maths Exam 1 that we did for our practice exam. Excellent, let's get to it. So the first question, constant force of F newtons is applied to a body of mass 10 kilograms parallel to a smooth inclined plane with angle of elevation theta as shown in this diagram. So part A showed that sine of theta is this third ratio. All right, so what's fundamental in this kind of problem is not to think it's too complicated, okay? We got to bring our minds back to basic trigonometry. We can see that the sine of an angle is equal to some ratio. Maybe that could be the opposite divided by the hypotenuse. So let's look at our diagram. Okay, well, we have sine of the angle is, we have a opposite side divided by a hypotenuse. Now hypotenuse is going to be the length of the incline, so we can use Pythagoras theorem. 1 squared plus the adjacent side squared, which is 49. Okay, so we get 1 over the square root of 50, and we rationalize it. 50 on 50. Okay, and we can see out of the 50, we're going to have from there, let's bring it down here, 2 lots of 25. So the square root of 25 brings 5 lots out of 50. All right, and finally, 5 into 50 gives us root 2 on 10. There we go. Nice, easy problem to begin with. So from that now, find the force F required to give the body an acceleration of square root 2 meters per second up the plane. Write your answer in the form of this expression where A and B are real numbers, G is the acceleration due to gravity. Okay, so we'll start by looking at all the forces that are sum to give us the mass times the acceleration. Okay, so there are two forces. One force is the force due to the weight force heading down the plane. So down the plane, the component of weight force is the sine theta component moving down the plane, and down the plane is opposite direction to the acceleration, which is heading up in the upwards direction, up the plane. Then we have force F, which is heading up the plane, and those two forces must sum to give you the total mass times the acceleration. So a mass of 10 kilograms multiplied by the acceleration, there we go. So from that, we're going to transpose and solve for F. So the force is given by the 10 root 2 plus, now we're going to add the weight term over to the right hand side. So this is a mass of 10 times G times sine of theta. And we think, oh, we're almost able to solve for F. We just don't know what sine of theta is. Well, you've got to make a connection. This is part B of the question. What was part A all about? Did we come up with a result for sine of the angle? Absolutely. Okay, so it was 10 root 2 plus 10 G, and sine of theta was square root on 10. Okay, so from that we have to express it into this form. So are there any common factors there? All right, we can simplify first. Factors of 10 will cancel, and then we'll have a square root of 2. It's outside of a 10 plus G in Newton. Without a part A, part B, or part C questions, they are connected to each other. So we need to always link back to the previous question. Let's do the next part. All right, find all possible values for the gradient of the curve. Sine x times sine y is equal to a half at the points where x equals pi on 4 across this domain for y between 0 to pi on 2, or 2 pi. Alright, so the job here is finding the gradient of a curve. So that's a differentiation process. So this curve we have is a relation, and relations need to be differentiated using a implicit differentiation technique. So take the derivative of the curve on both sides. Is equal to the derivative on the right hand side. Alright, so now we've got to recognize I've got a product of two functions. When I differentiate, I have to use the product rule. So the derivative of the first derivative of sine goes to cos of x multiplied by the second function. Okay, plus the first function multiplied by the derivative of the second, sine y. Now, I have to keep in mind I'm differentiating a function of y with respect to x. Okay, now the process is I must first go ahead and find the derivative with respect to y, then find dy dx. So this goes to cos of y multiplied by the derivative, dy dx. And that's going to equal to a 0 being the derivative of just a half. So let's transpose for dy dx. Okay, so subtract this first term over the other side. It'll become negative overall. Then we're going to divide by the sine x cos y to get the dy dx by itself. Cos of x sine of y on sine of x cos of y. There we go. Alright. So from there, we want to figure out what are the possible values of this gradient when x is equal to pi on 4. But the thing is, we also have the dy dx, the gradient depending on y. Okay? So we've got to figure out what are those y values when x is a pi on 4. Alright, so from there, before we go do that, let's recognize we can write our gradient function a slightly more simple way. And we can see we've got a cos of x divided sine of x. Well, that's a cot function. And we've got a tan function in y. Okay, so let's figure out what's going to be the corresponding y coordinate when x is pi on 4. We're going to substitute that back into the original curve and solve for y. So sine of pi on 4 times sine of y is equal to a half. Okay, so what would sine of y be equal to? So it's a half multiplied by, now sine of pi on 4 is root 2 on 2, so I'm going to multiply it by 2, divide by the square root 2, and from that, therefore, the y values will be, we can see where this goes down to, simplify down to a root 2 on 2, and the inverse sine of root 2 and 2 is a pi on 4 in the first quadrant. But if we bring our thinking back to the unit circle, and you can always draw little unit circle diagrams to help you remember the different values of angle in different quadrants. Sine functions are positive in the first quadrant, the sine functions are positive in the second quadrant. So what's the pi on 4 angle in the second quadrant? That's 3 pi on 4. There's that second value of y, and we've got to use both. So we've got 2 points, and we're told we're going to get 2 points because we've got plural for values there in the question. So you've got to pick up those little hints as to what to expect. Alright, so at the first point, pi on 4 and when y is pi on 4. Okay, then the gradient function okay, so cot of pi on 4 multiplied by, this is the negative cot being the correct gradient function, tan of pi on 4. Cot of pi on 4 is a 1. Tan of pi on 4 is also 1, so we get the value gradient for -1. Alright, what about at the second point? At pi on 4, 3 pi on 4. Okay, then the gradient value, dy dx. So we've got cot at pi on 4, but the tan function now is at the y coordinate, 3 pi on 4. -1. The tangent at 3 pi on 4, the 3 pi on 4 is in the second quadrant. We can look at unit circle again, and we know tan's going to be negative in that second quadrant, so -1. And altogether we get +1 as the gradient value. Alright, so important thing to realize, with implicit differentiation, if we have one known value of x, if we wanted to work out the corresponding y coordinate, we've got to substitute it back into the original relation, and then use those x and y values to evaluate your gradient function, which may also be in terms of x and y. Okay, so our next question. Solve this equation, it's a complex number equation, z cubed is equal to this 1 minus I all to the power of 6 for z, and we've got to write the solutions in Cartesian form. Okay, well there's two parts to this. The first part is we want to be able to simplify and evaluate that right hand side, and then set it up in polar form, ready to solve this complex root problem. Alright, so first off, the 1 minus I as a complex number, well, the modulus will be the Pythagorean of this, which will give us square root of 1 squared plus 1 squared times the cis function of the argument of this 1 minus I. So our argument is, we can find that using an inverse tan ratio perhaps, that just taking the number straight from this, so we get -1 in the imaginary, divide 1 in the real, so we can check where to see whereabouts that is in the Argand diagram. -1 in the imaginary, so it's downwards, positive in the real, down here in the fourth quadrant, and that's going to give us a negative pi on 4 angle. Okay. Alright, so from that now, we're going to evaluate that, that to the power of 6. So we can use Demoivre's theorem, where it's essentially the same as the polar form of it, to the power of 6, and that will go to this root 2 to the power of 6 times cis of this minus, and have as a multiple of 6 on the argument. Okay, what does that simplify down to? Well, the root 2 to the power of 6, that is an 8, yeah, and this simplifies down to 3 pi on 2 as a simple argument. Okay, now from that, let's set up our complex polynomial equation we're trying to solve. So z cubed is going to be the same as this 8 cis of minus 3 pi on 2. Now, to be able to compare parts of these complex numbers, we want the left-hand side to also be expressed in a polar form. So we've got the modulus of z, cis of the argument of z to the power of 3 is equal to the right-hand side. Okay, now on the left-hand side we can apply Demoivre's theorem, And this allows us to then identify that the modulus of z cubed on the left, well, that should also be the same as the modulus of the polar number on the right hand side, 8. So from that, the modulus of z must be the cube root of 8, which is a 2. Okay. And then what about the argument? So the Miles theorem will have 3 multiples of theta, so therefore 3 theta, well, that must be the same as the argument on the right hand side, this minus 3 pi on 2, okay, but this is just an angle, but the position in complex space could be any multiple revolution at that same position. So we're going to add on multiples of 2 pi, where k is just some integer. And it's important to put that notation down when we're defining k. Alright, so from there, let's simplify this a little bit more. We could get a common denominator and we'll end up with a 4k minus 3 as an overall multiple of a pi on 2. And so theta, as a simple rule now, will end up being divided by 3, and we're going to have pi on 6 angles with this multiple in the numerator. Okay, so from that now we're going to put them all together and determine all our complex roots. So the first one, z1, that's when k is 0. Okay, so it's going to take the modulus, the 2, cis of the argument. So we look at our argument rule. When we have k is 0, then we've got this minus 3 lots of pi on 6. Okay, and we can see that goes down to a pi on 2, or a negative pi on 2. Okay, so let's turn that into a Cartesian form. So we have 2 lots of, now we're going to evaluate it at cos and then at sine. So the cos of that angle is going to give us a 0 plus I times, and the sine of that angle. Okay, the sine of that angle will go to, this is down in the 4th quadrant at the bottom, so that will be a minus 1. Okay, and that simplifies down to negative 2 in the I, so there's 1 root. Okay, second one, Z2, 2 cis. Okay, now this is found on this rule now when k is 1. So if we put a k equals 1 there, we're going to have a 4 minus 3, which is a multiple of 1 of pi on 6. And let's evaluate it. Cos of pi on 6, okay, that gives us root 3 on 2, and sine of pi on 6 is a half in the I. Okay, and we expand, multiply by 2, and we get root 3 plus I as our second root. One more. Z3, 2, cis of the angle. So this is now when k is equal to 2. So 4 lots of 2, which is 8, take 3, gives us 5. So we've got 5 lots of root pi on 6. Okay, that's way over there in the second quadrant. So cos of a pi on 6, or 5 pi on 6 in that second quadrant is negative, same value, but the sign is still positive, second quadrant is still positive, so it's positive a half in the I, multiply by 2, and we get this negative root 3 plus I as our third root. And there we have our solutions for this equation in Cartesian form. All right. Okay, and we're back for question 4. It's a vector question. So in this triangle, O to A to B, there is point P be the midpoint of A to B, so midpoint means half, and Q be a point on O to B, this line segment, according to that ratio. So QB is twice O to Q. So from there to there is twice as long as this segment, then that is one part and that is two parts. So altogether, we've got a fraction of a third there. So one thing we can note, perhaps O to Q is going to be a third of the whole line segment O to B. So that could be an extra piece of information we can derive from this statement here. So then let X be the point of intersection on A to Q and O to P. Right there, those diagonals. Okay. Given that vector A is O to A and B is O to B, express A to Q in terms of A and B. All right, so A to Q. Well, we can get there by going A to Q is the same as A to O, which is negative A, plus O to Q. All right. Now, O to Q, as we established, was a third of O to B. So we've got negative vector A plus a third of going from O to B. There we have it. So there's our expression for vector A to Q in terms of A and B. So then part B says, express OP in terms of A to B. All right, next one, O to P. All right. Well, point P is the midpoint. So that might be A to P being a midpoint segment from there to there. Well, that's just a half of A to B. That's what we can state from the definition of a midpoint. All right, so let's try it. O to P. Going from O to P, first we could go up to from O up to A. And then we can go from A to P. All right, well, O to A we know, that's vector A. A to P was half of A to B. So we've got A vector plus half of A to B. Okay, now if we went from A to B, it's the same as running backwards along vector A and then we add on to that vector B. So we get vector A plus a half of running backwards along vector A, which is negative A vector, plus vector B. Now we can simplify that. Okay, so therefore we've got O to P. All right, so we've got one lot of vector A and we're subtracting a half. So we'll get a half of vector A and vector B. There we have that vector, O to P. All right, now what do we do next? Now, let K be the rational number such that A to X is some rational fraction of A to Q. All right, so we have this part, A to Q, from the previous question, part A. So let's start there. A to X is going to be some multiple of A to Q. Now, A to Q was, from part A, a third of B minus vector A. Okay. But what's another way we could form A to X? Well, if we've got some unknown relationship, we want to be able to compare this right-hand side form of the vector to a different form of the vector, and we can equate the coefficients of the vectors to work out what should be the size of the parameter K. So let's look at another way in which we can construct. this vector a to x. So if you look back at the diagram, what is a to x? Well, going from vector a to x, well, we could run backwards along a and then go from o to x. Now o to x is along this line segment o to p. So that is suggesting that this o to x is going to be some fraction or some ratio of o to p. So that's very similar to a to x being some fraction of a to q. All right. So let's draw on that. Running backwards along a. And then we have from o to a and then o to x. Well, that's vector a. Now o to x was some amount of o to p. So we're going to represent that with a different parameter running from o to p. All right, and this parameter L is just some positive real number. All right. Now, O to P is what is a fraction, is a vector we've already established. So from part B, we have that being. All right. So we've got half of A plus B. So there's the half. Vector A plus vector B. All right, now let's see if we can collect some of our vectors together. Well, this will give us L on 2 minus 1 whole of vector A plus L on 2 of vector B. Well, that's another expression for vector A to x, which is also the same as the one above. So we're going to go ahead and equate the two forms of this vector. So all together now, we've got this negative k of vector A plus k on 3 of vector B on the left. Well, that's the same as and L on 2 minus 1 of vector A plus L on 2 of vector B. All right, so therefore, what does that mean? Let's see what we get. By equating the two, well, we've got negative k must be the same as an L on 2 minus 1 by equating the coefficients of the scalar multiples of the A vector. We get this expression. All right, and what else do we have? Well, let's do the same for the B vector. K on 3 must be the same as an L on 2. Okay, so from that, we get an expression for K. K then must be the same as positive 1 minus L on 2. So if we can calculate what K is, as long as we work out what L is. All right, so let's continue. Let's see if we can solve them simultaneously. Now, we know this arrangement, so we can also get from number 2, so from 2, we get that K is equal to 3 on 2L. All right, so let's sub into 1. Down here is number 1. All right, so 3 on 2L is going to be the same as a 1 minus L on 2. Okay, almost there. So let's combine them. We get 2L is equal to 1. L is going to equal to a half. All right, now from that, let's sub that back into number 1. And so K will be 1 minus, now if L is a half, this number here says L divided 2. So a half of 2 it is. A half of a half there is a quarter. Therefore, K is 3/4. quarters as our result. All right, so this process of solving simultaneous equations, in this case a substitution approach, seems to be the most easy one to get into. And with these kinds of vector problems where you've got some unknown parameter, which is a multiple of another vector, we have to come up with two forms of the same type of vector, a to x, and that way we equate the left-hand side and the right-hand side and look at the common coefficients of those vectors. Okay, next problem, question 5. Sketch the graph of this arcsine of a half take x on the axes, and we've got to label the endpoints. Okay, so sketching the graph, you've got to consider what do we know for an exam 1 situation. We have to be able to know what the original arcsine graph is. It's just the standard arcsine shape. Maybe this is one of the shapes of the graphs we need to learn and remember. Okay, so standard arcsine graph. Well, maybe I don't really know what the arcsine graph is, but I know that it's going to be a function of x, and it's the inverse function of the sine graph. So for my inverse function to be a function itself, the original sine graph has to be a one-to-one mapping. So sine graph, for it to be one-to-one, has to be such that it's limited across the endpoints, across the turning or stationary points of our sine graph. So here's the continuation of the sine graph. And the endpoints closest to the origin are at the stationary points here, and we get the values pi on 2 goes to 1, and minus pi on 2 we go to a minus 1. So there's our standard sine. All right, so the inverse function for our standard inverse sine now, it's a flipping across the line y equals x. So this point here will flip up this way and down like so. So this coordinate now will be minus 1 in the x, minus pi on 2 in the y, and that coordinate there will be 1 pi on 2. Okay, and there's our inverse sine. So if we start with our basic graph, standard graph of the inverse sine function, so then we interpret the transformations that are acting on a regular inverse sine of x. So there's two transformations happening. One, there's a reflection. There's a reflection along the y-axis. So that's the negative, the minus on the x, a reflection over the y-axis. So that means this point up here, that's at positive 1 and pi on 2, well, then that's going to reflect over the y-axis like this, and it's going to be a minus 1 to get a pi on 2. All right, so it's going to flip this way. So after the first transformation, 1, it will look like this. Something like that. Now we've got a minus 1 pi on 2, and the positive 1 at minus pi on 2. Okay, so there's our arcsine of a negative x graph. Okay, and now what about the second transformation? Well, now we've got a horizontal shift of half units. Okay, and because of the reflection on the x coordinate, this horizontal shift by half units is going to happen to the right. It's going to shift by half units to the right towards the positive x now. Okay, so that means that instead of having the pi on 2 happening at minus 1, it's going to be adding, it's going to happen at minus a half. So minus a half is there, and we're going to get a pi on 2. So lining it up on the main graph, we're going to put an endpoint here. And I'm going to have at minus a half pi on 2. All right. Then the second endpoint down here occurred at 1, but because we're shifting half units to the right towards positive x, we're going to add a half onto it. So it's going to be 1.5, or 3 on 2. So at 3 on 2, which is over here, we're going to get a negative a half. And the whole thing's going to shift this way. And here, with the original graph, intersect at the origin. Now it's going to shift, that same point is going to shift by half units, so to the right. So it's going to intersect here. And the only other thing that we have is, as it comes down, it's going to cross through and looks like we're going to have a y-axis intercept. So we might want to determine that y-axis intercept. We're going to have a arc sine of a half minus x, and when y is 0, that's us determining x-axis intercept, not what we want. The y-intercept is when x is 0, that's right, so that's simply inverse sine of a half, okay, which is pi on 6. Pi on 6 is dividing the pi on 2, the 90 degrees, into thirds, so here. Okay, and we can label that 0 pi on 6. Alright, so down, 1, 2, oh. That's why very important we always have a rubber when we're working on these graphs. This one comes up this way. Boom, this way. Okay, there we go. There we go, not too bad. Okay, there's our by hand sketch of our arc sine graph. Now we have to find the exact volume of the solid obtained when the section of the graph of what we had looked at, where the section of the graph is greater than x equals 0, is rotated about the y-axis. So it's going to be bounded to the y-axis, where a positive y-axis when x is greater than 0. Okay, so let's visualize that region on the graph itself. So it's greater than x equals 0. So x equals 0 along here, along the y-axis. Okay, so that there's going to be our bound. Everything to the right of that has to be what we're looking at. Now the graph only tends up to this point here. So there and to there. So it seems to be this is our region where greater than x equals 0 that we're going to rotate about the y-axis. So by doing that, we're able to identify our main limits on our integral that we're going to form, minus pi on 2 to this one, which was our pi on 6. Okay, so a volume integral, pi at the limit, so the lower bound is minus pi on 2, upper bound is pi on 6 of, now it's got to be x as a function of y that is being squared, and we're integrating that with respect to y when we're doing a rotation around the y-axis. Okay, so we have to take our rule and transpose that for x. So where we have, we can do that over here. All right, so we will have half minus x is equal to the sine of y, and then x is going to equal to half minus the sine of y. There we go. All right, so that becomes our integral now. So the volume becomes pi on 2, pi on 6. So bracket, we've got two terms, half minus sine of y all squared. So before we can integrate that, we're going to have to expand out this bracket. Okay. So we get, well, quarter minus 2 lots of half times sine of y. So there we go, sine of y plus sine of y all squared. Square that dy. Okay. Now, that's integratable straight away. We can integrate sine of y, but we can't integrate the sine squared. But we can convert that into an expression in terms of single powers of power of ones of sines and coses using a double angle rule. So best one to use here is cosine. All right, so by rearranging the double angle rule on cos, we can get sine squared of y. Well, that will be 1 minus cos 2y on 2. Okay. All right, so now our volume becomes 6. Okay, so it goes to quarter minus sine of y. Now let's substitute this in for the sine squared. We've got plus quarter half minus half cos of 2y. And we integrate all that with respect to y, and now each term is achievable in doing so. Okay, so when we go through and carry out the integral, then we will get our resultant integral function here, 3/4 of y plus cos of y minus a quarter sine of 2y. And now we're ready to evaluate at the limits, pi on 6 and minus pi on 2. So when we substitute them all in and subtract and substitute the negative pi on 2 in, then this simplifies down to, if we add them all up, we will carefully see, we'll get okay, we've got pi on 8 and we're subtracting a negative 3 pi on 8. So there's 4 pi on 8 altogether, so that's pi on 2. All right, and then plus pi on 6, cos of pi on 6, well, they're root 3's on 2's. That goes to 0. That one goes to 0. As well, so that's good. Sine of pi on 3, well, that's also root 3 on 2. All right, so we will get a 3 root 3 on 8 altogether, and multiplying the pi through, pi squared on 2 plus 3 root 3 pi on 8, and these are a volume. This is a volume, so units cubed to get our result. Okay. Okay, statistics. This is a tricky one. So now it's all about breaking it down into the idea of, if we identify the random variable that we're working with, we got to then get the expected value and standard deviation of that random variable, and then think about what's the distribution on that random variable. All right, let's try. Two teams of soccer players are timed running 100-meter sprint. Team A's time are normally distributed. Okay, that's good. Mean of 14.7 seconds, standard deviation 0.8. Teams B are also normally distributed. 13.7 seconds, standard deviation of 0.6. Now we've got another random variable D, and that's also going to be normally distributed, okay, because A and B are drawn from a normal distribution. This represents the difference in times, and we're going to find the probability that the randomly selected player from Team A, now let's interpret this more carefully, Team A would be faster than randomly selected player from Team B. Team A would be faster than Team B. All right, so if that means the time for Team A will be less than the time for Team B. A time is less than the time for B. Okay, so if that's the case, what do we get for D? That means our random variable D must be less than 0. If A is less than B, then that becomes negative. So that's our first point of thinking we got to achieve is what's our value on our random variable D. So we want to find the probability of this happening. So what do we know about D? Well, first off, let's think about how D is constructed. It's from A and B. It's going to be normal. Okay, so we got to work out what's going to be its mean and standard deviation. All right, so the mean of D will be made from the mean of A minus the mean of B. Okay, so this comes from the linear transformations on random variable D. What can we say about, and so that will give us our 14.7 minus a 13.7, which is 1 second. All right, what about standard deviation on D? Well, the variances combined, isn't that right? The variance of D is the variance of A plus the variance of B. So that's the standard deviation squared. So to get the standard deviation of D, I'm square rooting standard deviation squared of A plus standard deviation squared of B. It's like the Pythagorean sum, isn't it, of those two standard deviations. All right, so what do we get? Well, 0.8 and 0.6. I'm going to express them in fraction form. 0.8 is 8 on 10, all squared, plus 0.6, 6 on 10. All right, working with fractions allows you to think about it in terms of whole number. We don't have to worry about positions of decimal places in that way. So what would this simplify down to? Well, I know that's 100 in the denominator, and I've got a 64 plus a 36, which is also 100. 100 divided 100 is 1. Nice. All right, so what does that tell us about D? Well, variable D is normally distributed with a mean of 1 and a variance of 1 unit. So there's our distribution. So our job now is to think about, well, what's the probability that D is less than 0? Right, well, I think I need a calculator to use my binomial CDF function. But not necessarily, this is exam 1. How else can I think about it? Let's draw on what we know about the standard normal curve. Okay, so now let's convert to Z, standard normal curve. Let's get pronumeral Z happening, random variable Z. So that's going to be found by the value of D, all right, which is going to be 0, minus its mean, 1, divided by its standard deviation, 1. It's just -1. So evaluating this is the same as finding when Z is less than -1. That's just one standard deviation to the left. All right, so from there we can well, think about standard normal curve. Here's our little curve description. Z is 1, so between Z equals -1 and Z is equal to 1 standard deviation either side of the mean. How much is that altogether? Yeah, that's right, that's 68% of the area underneath the curve, 1 standard deviation either side of the mean. All right, so we want less than -1, so that's this little section here. So that there is half of the complement of this red area, 68%. So the complement is 1 minus 0.68. There we go. We want to find half of it. Aha. And we get 16%. Okay? And there we have our approximation for our probability. Now, next part. We're going to take a random sample now. If a random sample of 4 players is taken from each team, find probability that the average time for the four players of team A will be faster than the average time from the 4 players of team B. All right, so random sampling. Well, we're going to have to define a new variable. We've got sample averages or sample means, so then let the bar be the sample mean difference of the sample of A minus the sample of B. Okay? Alright, so then what do we know about each? Well, then this is also going to be normally distributed if it's drawn from the population, from a normally distributed population. So the mean of A is just going to be, well, that's just the mean of D. So the expectation value, the expected value on the sample is just the expected value on the population, isn't that right? Well, we got that to be a 1. All right, what about the standard deviation? Well, then what does that give us? We get the standard deviation on D divided by square root of how many is in the sample. We've got n equals 4 in the sample. We're going to divide the square root of 4. Yeah? So standard deviation of the population of differences D was 1, and now we're at 1 over 2, so we get a half. Yeah, okay, so now this is our new parameters. So our sample mean difference there is also normally distributed for mean 1, and variance of a quarter. So we want to know the same thing, probability that team A will be faster than the average of team B, so that's the same idea. Where B hat is less than 0. If A is fast, that means A is less than B. B is negative. And again, we're going to convert that to Z. So what is our Z score? So for our D hat value, minus the mean divided by the standard deviation, which is now half. So it's a different value now. So it's -2. All right. So if that's the case, this probability on D is the same as this probability on Z. 2 standard deviations to the left. All right, well, let's see what this looks like and remind us about the symmetries of the standard normal curve. Well, if we had 2 standard deviations on either side of the mean of 0, so Z is -2 and Z is equal to +2, then this area here gives us how much? Right, if we remember, it's approximately 95%, 2 standard deviations either side of the mean. So then, less than this value, we're looking about this little area here. Well, the complement probability must be 5%, and this is going to be half of 5%. So therefore, what we have, probability that Z is less than this value, 1 minus 0.95 divided by 2, and we get 2.5%. There we go. Okay, question 7. This one was a tricky one. So Position of a particle at time t is given by this position vector. Well, that looks pretty complicated, position vector. Alright, so we have to break it down very carefully. Find the gradient of the path followed by the particle when t is 3. So the gradient of the path, well, the path being the Cartesian equation. So that is as a function, it might be y as a function of x, or it might be some xy relation that constructs the path. So the gradient of that is going to be our dy dx, the steepness or the rise of the run of the path itself. Okay, so we're determining dy dx. So from the position vector, this function here is our x function of t, and this function here is our y function of t. So based on that, we're looking at combining those two to get an overall dy dx. So our derivative with respect to y multiplied by derivative of x with respect to t, like so, combined together in a chain rule. Well, that will give us our gradient of the path, dy dx. Alright, so that means I got to differentiate each of those two functions. Now, if I think about it carefully, inside my arctan function, I've got a 2 times t squared. Well, that's like a little parabola. So I've got a little quadratic. I've got a quadratic equation inside an arctan equation. So that's a composite function. And when I differentiate a composite function, I got to do the chain rule. So this is like a chain rule inside chain rule. Oh, wow. So let's think about how we're going to break that down. Well, let's pull this position vector apart and name it as different functions. So x is equal to the arctan of our 2t squared. All right. Well, let's go ahead and pull this apart again, and let u is equal to this inside function, this 2t squared. All right. And so now our x becomes just a function of u. So now there's my simple function, my arctan function by itself, and I've got my small quadratic function by itself. Yeah, let's do the same for the y equation. Okay, now let's pull that apart. Let's call that something else. Let's use a w. I'm thinking what I'll do, I'll just take the top part, just the square root t function, because the divide 2 is part of that general structure of the derivative of the arc cos. So I get this. All right, so then y is just the inverse cos of a w on 2. All right, so now I've got 4 little standard equations on their own. So the chain rule, applying the chain rule to them, well, what will this become? My dy dt, derivative of the y function with respect to t, well, applying the chain rule, that will be a dy dw multiplied by dw dt. Okay, multiplied by, and then I've got my dx dt. Ooh, should be reciprocal of that, shouldn't it? Go ahead and got my thing upside down. Okay, let's fix that while I caught it. See, everyone makes mistakes, but it's important to pick up your mistakes and try and rectify it. There we go, that's better. Now that's the correct structure or rearrangement for the correct chain rule, isn't it? So this is the reciprocal of dx dt, so I'll 1 over the reciprocal. Now my dx dt, well, that can be found as dx du dot du dt. There we have it. So 1, 2, 3, 4 derivatives I'm going to plug all together and combine them that way to get my gradient of the path. Alright, so let's get our 4 derivatives. Alright, so first our dx du will go to a 1 on 1 plus u squared. Okay? Alright, what about dy dw? Okay, well, that's a negative 1 on square root of, now this is a 4 minus w squared. Okay, very good. What about u and w? So du dt. Alright, well that's just a 4t, that's an easy one. And then what about dw dt? Okay, well that goes to 1 over 2 root t. Perfect. There's our 4 derivative parts. Alright, so let's all plug that back in together. So dy dw, that's this one. Negative 1 on square root of 4 minus w squared, but w is square root of t, so I square that and I get minus t. Okay, multiplied by dw dt. So this expression 1 over 2 root t. Okay, multiplied by, alright, now set this up carefully. 1 over, alright, dx du. So dx du is this bit here. So 1 over 1 plus u squared. But u is 2t squared. So I got to square that. Right. Goes to 4t to the power of 4. Aha. Multiplied by du dt, which is just 4t. There we have it. Okay, so we start working at tidying it up, and what will that go towards? Well, we'll get a minus 1 plus 4t all on, we'll have an 8t square root, and this part here, there's 4t minus t squared. Beautiful. Okay, so there's our gradient of the path. So from that, bit of a hard slog, but we got there. Got to be switched on with knowing your derivatives and when to go about applying your chain rule correctly. Okay, so the last part to get our derivative, at a point we got to substitute t equals 3 and do some by hand numeracy. And you're going to just lay it out very carefully and not rush the calculation. So here we go, we're going to substitute t is equal to 3, and therefore y dx is equal to, alright, 1 plus 4 lots of 3 to the power of 4. Okay, and then we've got 8 lots of 3, and square root, okay, 3 minus 3 squared. Alright, so first we're just going to do one bit at a time. 3 to the power of 4, okay, well 3 squared is 9, and then 9 squared is 81. So we've got 1 plus 4 lots of 81. So timesing going forward is like doubling and then doubling again. So if we double 81, we get 162, double that again, plus 1. So what should we end up with there? Negative, by the way. 324 plus that one more, which is 25. Cool, that was a hard one. Okay, 24. Root, okay, so this is 12 and we're minusing 9. Alright, all together, this is negative 325 on this value, 24 root 3. You have it. Okay. Very good. Well, let's move on. Question 8. Now we're finding stationary points. We got to find values of x for any stationary points of f, or show that none exist. Well, if we look at f, it's not too terrible as a function, but there's the domain, and it's a restricted domain for positive x values only. So it's going to be positive real numbers. The x values are going to be greater than 0, but we're going to exclude number 2 out of that. Okay? So to show that no points exist, that could only be 2 scenarios that we could get. Well, our stationary points is when the function, the derivative of the function is equal to 0, and when we solve that equation, we're finding locations of stationary points. But if none exist, that means we get no real solutions. Okay, for stationary points, or we get real solutions, but they lie outside the domain. So the real solutions are outside domain. Now, when looking at the function of x, solving something like that, doing the derivative, maybe a quotient rule, solving and equating it to 0, solving for x, I'm thinking the second option is likely to be the case if none exists. That is. Alright, let's try it. So, the quotient rule, we want to differentiate our function, the square root of x, over x minus 2, maybe using the quotient rule. So we've got two functions. Let our top function equal to u, get its derivative. Let the bottom function equal to x minus 2, work out its derivative, which is just 1, which is nice and easy. Alright, let's put them together. Now we should remember our quotient rule quite well. It says, alright, it's start with the v times u dash term minus u times v dash divided v squared. So we're going to get this term here, x minus 2 multiplied by 1 over 2 square root x minus just square root x all on v squared, x minus 2 all squared. Okay, so if we form a common denominator, then this fraction, this 2 times square root of x, is the extra factors which will pop down in the denominator here. X minus 2 all squared overall is your denominator. So we'll have x minus 2, subtract, we've got to get the square root x with this denominator first of a 2 square root x. So we have to multiply by that onto our square root of x. If it goes 2 times the square root of x times square root of x, is just full amount x. You can see this goes to negative x minus 2 over. Okay. So when do we get stationary points? Well, alright, so the derivative will equal to 0 when in fact just the numerator part of this fraction will equal to 0. Well, that's when x is equal to negative 2. Okay, so there's our stationary point. However, this is where we got to check it now against the domain. When we have a look at the domain, it says it's got to be greater than 0, or that's defined for our function. So it's outside the domain. Oh dear. So that means this element -2, okay, that's not an element of our domain. Some notation to explain it. All right, and then we can say no stationary points exist. All right, there we have it. Okay, now the next part, it's even funner. Okay, but we're going to draw on and remember this as our derivative. So now let's find x values for any points of inflection. We'll show that none exist. Right, so this is the second derivative, and the derivative of the derivative is equal to 0. Alright, so derivative of our rule. Now, what was that derivative? Let's have a look. Let's write that down, shall we? We had -x minus 2, then 2 square root of x, and then there was a x minus 2 all squared. Alright, well this is going to get tricky. So, before we tackle it, let's see if we can tidy it up a little bit. Well, there's a common factor there. I could pull out -1/2. That makes it a little bit easier because at least now I've got a negative I don't have to worry about, and I've got this factor of 2 that's half that I also don't have to worry about. And I've just got this x plus 2, and then this square root x minus 2 all squared. Alright, well I'm going to need to get the derivative of my denominator in all this as well. So that's going to be a little product rule I have to do. And again, it's going to be like a quotient rule overall. Alright, so let's set it up. So let u is equal to x plus 2, top function. Alright, nice and easy. Let b equals to the bottom function. Alright, now this derivative is where we're going to implement a little product rule, differentiation. So it's going to be the derivative of the first multiplied by the second function, like so. Okay, then we're going to have plus derivative of the second multiplied by the first, so we'll have a 2 square root x of an x minus 2. Okay, there's our v dash. Alright, so let's put it together. Therefore, our second derivative of f, altogether what do we get? We're going to start with the v function. We're doing a quotient rule. So square root of x minus 2 all squared multiplied by the u dash function, which is number 1. Ooh, nice. Subtract u times v dash. X plus 2 multiplied by all this. Not fun. Alright, 1 over 2 square root x minus 2 plus 2 square root x minus 2. All on v squared. This squared at the bottom, so it'll be x x minus 2 to the power of 4. Huh. Nice D. Alright, well, any way we can simplify it. Well, I'm thinking I want to go try and cancel out common factors straight away. Well, what factors do I have? I'm going to look for the x minus 2 bracket factor. I've got a x minus 2 in the denominator, but I've got one here in this term, x minus 2. That's an x plus 2, so it's not the same. That's also going to multiply here. Here's the x minus 2 in that factor, and I've got an x minus 2 there. So x minus 2 bracket in every term. I'm going to divide that and get rid of it. Alright, so what's left? I'll have square root of x minus 2. Kill one of them. Okay, and then minus. Now I've got this 1 over 2 root x still there. I'm not going to touch that yet. Then I've got this x plus 2. That's going to multiply one of these x minus 2. So let's put that in. And I know that's like a difference of 2 squares, so I can express that as a x squared minus 4 straight away, which is that multiplied by one of those brackets because I divided the other one. And then I'm distributing this negative across, so subtract the gain. And now it's a 2 root x times x plus 2, because this one divided out of the way. Very good. Okay, that was a good simplification. Now that's x on x minus 2. Power 3. Okay. Alright, how else can I simplify it out? Well, now if I look at the numerator, I've got the square root of x in each term as well. So how can I simplify that a little further? What trick could I come up with to help me get rid of this? Well, what about if I take multiply by the number 1 and square root of x on the square root of x, and then I'll distribute this root x throughout the numerator. What will I get there? Well, that'll be a x on the first term, this root x times this term over here, x minus 2, minus square roots will cancel here, so I've just got a half x squared minus 4, subtract 2x of x plus 2, all on, now this is an x root x of an x minus 2 cubed, coming along. Okay, alright, so from there, what we're looking for now are points of inflection. Okay, I want to see if, when does this go to 0? Alright, well, same idea as when the numerator goes to 0. So, second derivative equals 0 when my numerator goes to 0. So when I've got an x squared minus 2x, I'm going to expand it out, minus half x squared plus 2 minus 2x squared, subtract 4x equals 0. Alright, so I've gone from a horrible quotient to now quadratic. Not too bad. Alright, how was this simplified down to? Alright, so I get a more simple quadratic, and if I work at getting this by itself, so I'm going to do a little trick now. I'm going to multiply by, to help me simplify this, a negative 2/3, perhaps. So I get x squared by itself. Now this will go to a 4x, and this one will go to a minus 4/3 equals 0. Okay, so from there we're looking at this is quadratic, and whose solutions for x I can find by maybe completing the square. So I can see this can give me an x plus 2 all squared, and then subtract this 4 on 3 is equal to 0. Alright, and I'm getting different solutions for x here. So when I solve this, that will give me a 2 plus or minus the 4 on root 3 overall. Okay, will any exist? I got to check my solutions against the domain, the same as last time. So do I have, which one is greater than 0? Because it's got to be a positive real number, therefore only one of them. X equals 2 plus the 4 on root 3 is a point of inflection. Point of inflection. Okay, we got to make sure we check the solutions against the domain and state which one's the correct one. Alright, well, almost there. This is a killer. Last question. Find an antiderivative for the function g, where g is this log of mod x minus 1 on x minus 1. Okay, antiderivative. I'm doing an integral. And I've got, looks like two functions. It's like a product rule, or maybe I'm looking for the structure for integrals. I'm looking for using a substitution method of integration. So I'm looking for a derivative that multiplies a function that could be substituted for a smaller part like u. So, okay, I know that 1 over x minus 1, that's like a derivative of log. So what about if I let u is equal to the log of the modulus of x, and so then du dx will give a 1 over x minus 1. There it is. Okay, and so then the du part by itself is this, get this 1 over x minus 1 times dx, and that gives me my du part. So the integral of log base e x minus 1 over x minus 1 dx, then that becomes an integral on u with respect to u. Nice easy one. Okay, that will go to half u squared plus c, of course, but since we're finding an antiderivative, we're going to let c is equal to 0. Alright, substitute u back in, and we get a half bracket natural log of x minus 1 all squared. There's our antiderivative. Yeah? Find x-intercept for the function. X-intercept. X-intercept is when we make y is equal to 0. Okay, so x-intercepts is when we get log of x minus 1 on x minus 1 goes to 0. So only the numerator will equate to 0. Therefore, we're solving the natural log of modulus x minus 1 is equal to 0. Okay, so from here, to solve for x, we go to transpose. We have to do the inverse function to the natural log. So that means the x minus 1. Now, this is still the modulus of x minus 1. And that's something that shouldn't be just forgotten about or ignored or neglected. It is an actual operation, a function acting on x. We don't know what x is. X is assumed to be all real numbers. Okay, so that means this could be negative even. But now the modulus of x minus 1 is the value of e to the 0, which is the number 1. Okay, so what is the effect of the modulus of this? Well, this gives you two possibilities now. Well, it's when x minus 1 is positive overall. Okay, when that is a positive value overall, then the modulus returns just the positive of it. When that is equal to 1, and that means x is equal to 2. But at the same time, what about when the x minus 1 is negative overall? Well, in that situation, the modulus gives you the negative of it, like so. And that is equal to 1. So now what does x equal? Yeah? It's going to go to a 0. And there are two x-intercepts, plural. And in the question it tells us we're finding a plural number of x-intercepts 2. And that's precisely what the little key things we're going to look for in the question that tell us little hints of how many solutions we're looking for. Okay, very important thing to not neglect is that modulus function. Okay, so then what's next? Find an area. Find the area bound by the function. All right. And the x-axis and the line x equals minus 2. All right, so an area of this function, we're going to be doing a integral of log e of the modulus x minus 1 over x minus 1 dx. All right, so we know what the antiderivative is going to be. We don't know what the graph looks like, and we don't have any means to figure out the graph, so we're just going to have to think about the region by examining the type of numbers we have. We're told it bounds with the x-axis, so we know where those intersects are. X equals 0, x equals 2, so we've got that information. And with a different line of x equals minus 2. So that's to the left. That's to the left of the origin, which is x equals 0. So the graph is going to move, if it moves over to the left, which it will because it's got the modulus sign. When x is positive, this log of the, when x is in the negatives, then the modulus here makes it positive overall, so the log of that will be real. Alright, so what we will see is that the most minimum limit will be the smallest negative, which is down there in the negative 2. And then we integrate up to the bound with the x-axis, and that's at the origin, 0. Okay? So these numbers, between minus 2 to 0, they're all negative numbers. What will be the overall value of our function? Where is this going to be? We know it could be above the graph or it could be below the graph. And that's going to affect what we use for the area. So if we look at the denominator, if we put negative numbers here in the x, negative numbers minus 1, it's going to be overall negative. We will get log of this will always return positive values unless we have it in terms of fractions. So that means x has to be smaller than 1, which is not, it's much bigger. Okay, so I think it's going to be negative overall. It's going to be below the graph because in your denominator that will always result in a negative value in between those two limits, minus 2 to 0. So we're going to have a negative area. Alright, so having identified that, we're going to perform our antiderivative. We've still got this negative area. Let's apply this negative area out the front. Let's deal with that straight away. Oh yeah, sorry. Let's get the integral to absorb the negative, and so our integral now becomes from 0 to a minus 2. Okay, like so. And the antiderivative was this half natural log modulus x minus 1 modulus all squared. We're going to evaluate that from 0 to minus 2. Well, let's just take this half out. So we'll have log modulus of a minus 3 all squared. Subtract log modulus of minus 1 all squared. Okay, now this, we know this last part, log of 1 will be a 0, and log of modulus minus 3 goes to positive 3. So we've got this half bracket log e of 3 all squared. And there we have it as our units squared of area. Fantastic.